Ladies and gentlemen, this is going to be a special episode. In this video, we are going to prove Green's theorem in the plane. I think those of you who have heard of this theorem before know that this theorem is underlying the definitions of important vector operations, especially in vector calculus. If you want to learn about vector calculus, your knowledge will be incomplete if you haven't learned about the Green's theorem in the plane and its proof. So I suggest you take this video very, very seriously, and at least for the sake of your understanding vector calculus and its application, or just purely out of mathematical interest, you should learn this theorem and its proof and make your mathematical journey into vector calculus worthy. And let's get into it. First of all, here we can see the statement of the theorem. The statement simply reads, let there be two functions. Both functions are functions of two variables. Specifically, the settings we are talking about, we have a plane and the variables x and y. So we specifically have chosen Cartesian coordinate. Now, we can go from this coordinate-dependent description to coordinate independent description in two separate ways, and those, as I have explained, relates to important vector operations. So the fact that we are talking in terms of Cartesian coordinates in a plane does not make it any less general. This is most general in the plane nonetheless. So our two functions p and q, which are written by capital P and capital Q, are functions of x and y variables. Both of these functions have to be continuous, and they should also have continuous partial derivatives in all of their variables. Now, when this is the case, then we have to choose the region. Now, the fact that these functions need to be continuous and their partial derivatives need to be continuous has to be valid everywhere in the chosen region, which we shall call R, and on the boundary C. So the boundary of the region R is C. Then for both simply connected and multiply connected means that where there are 2 points, any 2 points in the region R can be connected by all possible continuously deformable curves in that region. So I shall draw you the examples and then you'll understand what I'm talking about. But for both kind of regions, whether it's simply connected or multiply connected, we have this theorem. On the left-hand side, we have a closed loop integral over the boundary of the region of p dx plus q dy. And this will have to follow this particular order, p with dx and q with dy. And if that is the case, then on the right-hand side, we have an open surface integral on the region R. The variables are, of course, both x and y because it's a surface integral, so we have dx dy, and the integrand is the partial derivative of q with respect to x minus the partial derivative of the partial derivative of the function p with respect to y. I just understood that I had a slip of my pen here all along. So once again, the integrand is the partial derivative of the function q with respect to the variable x minus the partial derivative of the function p with respect to y. As you can see on the left-hand side, p was accompanied by dx, and at the right-hand side, p was differentiated with respect to y. The left-hand side, q were accompanied by dy. On the right-hand side, q is differentiated with respect to x. And this is the statement of the theorem. Before I move on to proving the theorem, as I have promised, I should clarify the concept of simply connected and multiply connected regions. So on the left-hand side, we have the example of a simply connected region where the 2 points P and Q can be connected by continuously deformable curves. So this curve can be deformed into any shape that stays within the region, and this is true for all the curves. But if I come here where P and Q needs to be connected by a curve, we cannot continuously deform it without running into obstruction, because here, this region is not defined. It's not within the described region. So if you want to continuously deform it, you run into trouble in some case or cases where the curve needs to leave the defined region. So this is a multiply connected region, multiply connected, and this would be a simply connected region. We are going to prove our theorem for both of these two types of regions separately. First, of course, we start with the simpler case, which is the simply connected region, and then we move on to the multiply connected region and use the idea that we have derived for simply connected region. Let's get started. Okay, so here we have our first case where we have a simply connected region R and its boundary C. Now what we will do for the convenience of our proof is to divide the boundary into two parts, first in terms of x-axis and then in terms of the y-axis. How do we do that? Well, first we choose the points E and F in such a way so that we have two tangents parallel to the y-axis. These are tangents to the given curve C, and these two tangents intersect the x-axis at two different points, one of which we shall call small e, and the one from the uppercase F intersects the x-axis at the point lowercase f. Similarly, in the y-axis, we do similar thing. We choose the point D and H by choosing two tangents that are parallel to the x-axis and that intersect the y-axis at two different points, respectively at G and H. So now what we have done is to divide the boundary C according to the advantage that we can exploit by turning them into single-valued functions, specifically curves, that can be integrated with ease. What I mean by that will be manifesting as I go along. So bear with me. First, I take this curve E, G, F, right? And I look for the equation for this curve. Let that equation be y equals some function capital Y of 1 that is a function of x. I do the same for the other half, which is EHF, and let the equation for this curve be another function y2 of x. So this is the advantage that we are going to exploit, because otherwise the curve, that is the whole curve, could not be represented by one single function. So now that we have done it, now let's choose this integral here. So the integral, the surface integral of P dy, and we have the integration variables. Since the integrand is a partial derivative of P with respect to the variable y, the thing that makes sense to do is to integrate over the variable y first. And that is why what we are going to do is to bring dy closer to the integrand, and we should integrate over y first. Now, what will be the limit? Of course, the limit is going to be y equals capital Y 1 of x, and then y equals, the upper limit is going to be y2 of x. Now, that is the integration along the y, but then we have another variable. Because it's a surface integral, we have to integrate it twice with respect to two different variables. And what are the limits in the x variable are going to be? So I have dx outside. Of course, the x variable will only be enclosed within the points E to F, So therefore, this is going to be e as the lower limit and f point as the upper limit. Do you understand what we have just done here? So let me try to explain it again. What we started with is an integral, is a surface integral. So that means we have a function, we're integrating it over a surface, so we should get a number, right? Now the function that we're integrating over is a two-valued function. So when we integrate over y, the y here acts as the boundary. So that's why the upper boundary is the upper limit, which is y2, and the lower boundary is the lower limit. And when you integrate over y, it makes the integrand a single-valued function. And when you integrate over dx, you plug in numbers as limits, which in turn produce numbers. So that should make sense. Now, once you integrate this integrand over y, then that should be simple because it's been differentiated with respect to y and is being integrated with respect to y. So that should return the function p of xy, but in the place of y, you should plug in the limit. So therefore, what we find in the next line is this. So the integration sign over x should still prevail. So we have dx, but now the integrand, and notice we're going to write it a little bit differently. We're going to write the integrand after dx, the differential. And here we should get the function p, but the first variable is the variable x. The second variable in place of y, we should plug in the limit, which is y2, and then minus p of x y1. So this is after we have plugged in the y limit. All right? So now we have to integrate it over x. Now notice what happens. Now, what I can do in this circumstance is to write these two integrals separately and then switch the limits in one of them. So this is what I'm going to do. I'm going to write the first one as integral from e to f, all right, with a minus sign. So I'm going to write the second term first, and so I have p of x comma y1, right? So this is also a function of x, right? And then the next term is just simply plus, oh wait, I have forgotten to write dx. So I have dx p x comma y2 of x, right? So once again, this is going to be from e to f. But this is where the magic happens. I can write this by a minus sign, and to compensate for the minus sign, I switch the limits, so I write from f to e instead of from e to f, and the rest of it remains the same. It's a function p of x, and because y2 has also input x, overall it's a function of one variable, is the same function p on the first integral and p on the second integral. But notice what is happening. You go from e to f by one route, which is the lower limit, y1, and then you go from f to e by another route, which is the upper limit, right? So therefore, you have actually gone around the total boundary c once, and that's exactly a closed loop integral. So therefore, this whole thing can be written in one single line, which is equal to negative the closed loop integral on p times dx, and of course the closed loop is nothing but the boundary c. Alright? So this is fantastic. Now we can do the same thing for the other term, and we can find a similar result in a similar manner. So let's do it. Okay, so this time we go around the curve C in two different segments. Of course, first we'll have to go along the curve G, E, H, right? So that's the x1 part. So this curve will be described by the equation x equals capital X1 which is a function of y. So we are switching the roles now of x and y compared to the time we did before. And so that would be our lower limit, and GFH is going to be considered as the upper limit. So this part of the curve will be described by the equation x equals capital X2 of y. So once again, x and y have switched the roles. So these are the limits, the lower limit and the upper limit respectively for the integration along x. And then, of course, we integrate along y. So remember, the other term that we need to integrate, and this is the surface integral, once again, like before. But this time, the integrand is the partial derivative of q with respect to x, and we are taking a surface integral, so we have dx dy. So we divide it into two terms. This time, the inner integral of the first integral is along the x, and of course the second one will be along y. So what we have is dx, right, and the partial derivative of q with respect to x. The inner integral has limits, a lower limit and an upper limit. The lower limit is equal to capital X of 1, and the upper limit is equal to capital X of 2. And for y, the lower limit is going to be, well, remember these points, we had E and F along the x-axis, and, well, G and H along the y-axis. So since we're integrating over y, our variable just simply oscillates between G and H. So the lower limit is going to be y equals G, and the upper limit is going to be y equals H. And when we integrate as before, what we find is this. So integration from G to H dy, and in the integrand we have first the upper limit when substituted into the integral. So if you integrate this integrand with respect to x, you just get q back. So the upper limit is going to be q of x2, comma y, minus q of x1, comma y. And in a similar manner, we can separate them, change the limit so that it is equivalent of going around the boundary C1s, but this time we change the limit in the second term. So the negative sign, when flipped, the limit becomes positive to compensate for the switch in the limit, and so we find this equal to the closed loop integral of q dy. Alright? So the two results, when combined, becomes this. The first one gives us p dx, and we found that when we started from negative the surface integral of partial derivative of p with respect to y dx dy, and similarly for the latter case we have found q of dy equals, but this time we got a plus sign, so the surface integral dx dy, but the integrand with the partial derivative of q with respect to x. And when we combine them, we find the Green's theorem for simply connected domain. So this is kind of the first part of the proof, okay? But we are not done yet. We have exclusively proven this formula for a case where the region we are considering can only be intersected by the parallel lines at least once, but at most twice. So, for example, if I draw a parallel line parallel to the x-axis or the y-axis, we can see at most the line can intersect the boundary at 2 points. At least 1 point, at most 2 points. But what if it has a weird shape where the parallel lines, parallel compared to the axis can intersect the boundary in more than 2 points. So for example, we can have a field or a boundary like this, and then a parallel line would intersect the curve at 4 points, or 3 points, or 10 points, I don't know. Depends on the region. So this is what we need to consider next. So the simplest among the next complexity level is right here, where we still have a simple closed curve and a simply connected region. So remember, it's not yet multiply connected one. It's still simply connected, but this time a parallel line, a line parallel to the axis, whether it's the x-axis or y-axis, has the possibility of intersecting the boundary at more than 2 points. So this is how it's going to differ from the previous case. And the way we are going to solve this is by choosing what we call a crosscut. So notice on the boundary we have 2 points, S and T. We also have 2 other points, U here and V here. But S and T are special points in this regard. Why? Because when we connect them, then our region gets divided into 2 pieces. One is R1 and the other one is R2. Now the boundaries are also closed, right? And the 2 boundaries share the crosscut. But because the boundary is closed, you'll notice that on one side the boundary runs in one direction along the crosscut, and on the other side the boundary runs along the other direction along the crosscut. So we simply have to apply the previous situation, which we have just proven, in this figure twice for each part of the region. And remember, there is nothing wrong we are doing here because it's all still a simply connected region. So we can apply the previous case, which is the Green's theorem, for a case where a parallel line, a line parallel to the axis, can intersect the boundary at most 2 points. We just simply use that case in this situation, but twice, and that will prove our claim. Okay, so let's do it. So here we have written down the statement of the Green's theorem twice, because we have 2 separate regions. Of course, on the right-hand side, we are doing a area integral or a surface integral, so therefore we have dx dy. But this region, when used for R1, then the boundary of it, which should be specified on the left-hand side of the statement, is going to be S, T, and then U, and then comes back to S. Okay? So we go along the counterclockwise way. Alright, what about when we choose the area to be R2, or the region to be R2? In that case, the boundary of it should also go in the positive counterclockwise direction, and that is going to be S to V to T and then to S. So therefore, when we add up both sides, the right-hand side is going to give us R1 plus R2, which will give us the whole region R. But what about the left-hand side? So let's just make that clear. So after addition here, we have written the right-hand side first, and we will next write the left-hand side. But next, what we see is the sum of the 2 closed-loop integrals. Now, for the simplicity, what I'm going to do is to just write down the integral sign. Well, all of you will know what happens. So within the integral, we have the integrands and the differentials like this in all the cases. So I'm just going to write the integration with its limit. So the first one runs along S, T, U, S, and the second one runs along S, V, T, S. Now we can separate those. by dividing the trajectory into a couple of parts. So it's always a wise decision to keep the figure in front of us. Here we all need to separate the problematic part that is done by the crosscut, which is ST or TS. So from the first one, what we do is to separate the ST part, so the integral along ST, plus then we take the integral along the TUS part, and from the next one, we again separate the part of the original boundary and part of the crosscut. So the part of the original boundary is SVT, so we have SVT, but then the part of the crosscut, which becomes the new boundary, is simply TS. All right? Now, the important work has been done. We'll have to be a little bit careful just to finish this task off. What are clear to us are actually two things. Number one, the integral of ST gives the same one when taking the integral along TS, but these two are, well, carrying the opposite sign compared to each other. So this part is going to give us 0. What about the other two parts, the two original parts? Well, when they are combined, so we go from T to U to S, and then to S to V to T again, this, ladies and gentlemen, is going to give us back the original boundary, which is C. So therefore, this is simply TUSVT, which is simply the closed loop integral along C, which proves our original claim about the Green's theorem. So this equals the closed loop integral along C of P dx plus Q dy. That completes the proof of the Green's theorem in a simply connected region. Now, the final and the trickiest part, which is the Green's theorem, is to be shown to be valid in a multiply connected region where the characteristics of being multiply connected were discussed earlier in this video. Once again, DGFE is the boundary. Actually, it should be the other way around, EFGD, so that we are consistent in terms of the positive directedness of our boundary. So this is the inner boundary, that's why it goes in the other way around, right? In the clockwise direction. Of course, the outer boundary will be the counterclockwise direction, which is along the points H, A, L, K, J, and in between, we have our desired region R. Like before, we introduce a crosscut once again. And so once again, we have the right-hand side of our theorem, which claims that the surface integral of the partial derivative of Q with respect to X, so dQ dx minus dP dy, the partial derivative of P with respect to Y, and the surface integral is along the variables dx dy, is going to be, well, now we need to find out the boundary for the integral of P dx plus Q dy. Once again, this crosscut is going to help us because this crosscut helps us to divide. Well, technically it doesn't divide, it connects the two boundaries by the two crosscuts. Now that it connects it, which becomes the whole boundary, well, let me write it down so I think it should be clear to you. The whole boundary becomes positively oriented, and this is also why the internal boundary has to be oriented clockwise unlike the outer boundary, which is the counterclockwise, so that when we connect the crosscut, the whole boundary becomes one big counterclockwise positive-oriented boundary. And so after introducing the crosscut, we have, well, we have this. We have A, L, K, J, H, then once again A, then D, then E, then F, G, come back to D, and then come back to A. All right? Now, of course, the internal one can be called C2 and the external one can be called C1. Excuse me, that should be C1. Like this. It was a slip of the pen. And notice this is actually the combination of the two boundaries. How? Let me show you. So, like before, I'm just going to write down the integral sign and the limits, not the integrand really, because the integrand is right here, which is not going to change. So we have what? We have A, L, K, J, H, A. Right? So this is the outer boundary, which is C1. Then we have AD. Then we have, well, D, E, F, G, D, and then we have DA. Now, AD and DA, these two integrals are going to cancel each other. And this one, which is the internal boundary, and is of course going in the clockwise direction, is going to be C2. So the combination of those two are going to give you the original boundary, which is C, and C is just simply a combination of C1 and C2 oriented in the said way, which gives us back the Green's theorem for a multiply connected region, which completes our claim or the proof of our claim. Thank you very much for patiently waiting. And if you are at this point still listening to this video and watching it, you are truly a mathematics fan or a physics enthusiast for that matter. And congratulations, this is an achievement, a huge achievement for the science. And this is very inspiring as well. So don't forget to like, share, and subscribe. I will soon see you in more videos with more math and physics contents. Till then, take care. Bye-bye.